Okay. Hi, everyone. Thank you for attending to today's webinar. Today's speaker is Dr. Cui Tao. Dr. Cui Tao is an associate professor at the University of Texas Health Science Center School of Biomedical Informatics. Dr. Tao's background is in both computer science and biomedical informatics. She is an expert in medical informatics with focus on conceptual modeling, biomedical ontologies, terminologies, and semantic services. Dr. Tao has been working on applying ontology and semantic web technologies on clinical and translational studies in the past 10 years. She has extensive experience on ontology development and has been working on developing ontology-based approaches for clinical and biomedical research. She has also been working on consumer informatics, focusing on improving consumer health communications using semantic technologies. If everyone could please mute their microphones to avoid any background noise. And Dr. Tao, please feel free to go ahead and get started.
All right, thanks for the introduction. Good morning, everyone. Today I'm going to introduce a few projects we have been recently working on by using ontology and the semantic web technologies. So first, I would like to spend a few minutes to briefly introduce the idea about ontology and the semantic web, in case people are not familiar with them. So the idea about the semantic web was first introduced by Sir Tim Berners-Lee. He was also one of the original inventors of the World Wide Web that we are currently using. Their original vision about the web was much more ambitious than what we are having now. The original goal of the web was to make the content of the web more machine understandable and processable, so that computer agents can provide more intelligent ways to help us to complete a lot of tasks automatically for us, or to conduct more powerful data analysis for us. So the first paper about the semantic web was published about 16 years ago in the issue of Scientific American. So if anyone's interested, I recommend to read this article. It's not very long, but they did show a lot of different kind of examples of the vision, and quite a few examples are relevant to healthcare. So basically, the difference between the semantic web and the current web is currently we are organizing our information or data by documents. So let's see, for example, if we want to search for something, we either go to a search engine such as Google, or we may go to PubMed to search, research relevant scientific findings. And usually we just type in a keyword, and then a search engine such as Google will return us a lot of links. So in this case, I want to search for gene, and then Google gives me 600,000 links. So in order to find the answer I'm looking for, I still have to manually click different links and then read each document one by one carefully to find the information I'm looking for. Not to mention that this kind of keyword-based search is usually very ambiguous. So for example, I'm not sure if you can see my cursor here. So I'm pointing to the second link to the bottom. So this CDK4 is actually a short name for a book, not for the gene. So even if I found the page that contains the information I'm looking for, I'll still have to go through everything, pass out the information, so that I can find the answer of my question. Can you still see my screen?
Yes, we can.
Okay, so I got some network connection errors. What about now?
Yes, we can. Just put the presentation.
Okay. Yep. Okay. Let me go back. Okay. So what is the problem? Well, consider a typical web page. So this is a page about a conference, as we all can see. So usually, there might be markup. So for example, in this case, this is an HTML file, so which is a markup language. So there are some things that computer can render, like the font size, the colors, where to put the links, and etc. Same thing for PubMed articles. So PubMed usually provide metadata, the index, so that we the search engine has some clue what the article is about, the author's name, and etc. But deep semantics is usually only accessible to humans, but not easily to computers. So this is the information we can see. Even without the rendering information, we can still read the content because we understand English and we can figure out this is about a conference, where the conference was and when it was, and etc. But this is what a machine can see. So without understanding the semantics, a computer program can only treat these as a bunch of symbols. So what are we going to do? What can we offer? Basically, we want to give a computer a brain so that it can understand the semantics behind all the documents. And we use an ontology-based approach to do that. So this is sort of I call to add semantics to the document. Basically, we want to do semantic annotation with respect to a domain ontology. So the idea of the term ontology was actually adopted from philosophy. And in computer science and information technology, we can formally define an ontology to describe a specific domain by defining the concept within that domain, define the relationships between these concepts, and also we can define constraints. So that with an ontology, we can ensure semantic interoperability, across different websites or across different domains, and we can also do semantic reasoning to infer new knowledge based on what we have seen or what we have known, and we can also do consistent checking. So as we all know, there are a lot of biomedical ontologies out there. For example, the NCBio BioPortal currently hosts more than 600 biomedical ontologies, and these ontologies are widely used in different applications. So today I'm going to just share a few. So the major technologies we're using here, of course, are from computer science point of view are text mining, machine learning, NLP, and also conceptualization, ontology, and knowledge-based creation. So these two technologies sort of are interwoven together. Basically, with NLP and machine learning and text mining, we can try to build a knowledge-based or an ontology automatically or semi-automatically at least. But also with ontology's help, we can also do semantic annotation through different documents using NLP technologies. So here are the projects I'm going to introduce today. So the first is called TAMR, Temporal Relation Modeling, Extraction, and Reasoning. And also I'm going to discuss two different applications for TAMR. One is regarding to patient safety analysis, and the other one is about clinical trial eligibility criteria representation. And if time allows, I will also talk a little bit about how we use ontology for patient education. Okay, so I want to introduce the TAMR project. Basically, we want to semantically represent the patient medical history. So as we all know, the time dimension is important in clinical research. the EHR data, for example, by nature is historical. So if we can efficiently and temporally provide or uncover the temporal patterns hidden in the EHR data, it will allow us to do a lot of different kinds of data analysis. So basically, what we want to do here is we want to see the temporal pattern both on disease level or patient level, so that we can explain why a disease happened or to predict future events, for example, such as adverse events. We want to do it on different level of granularity. So on individual patient level, if we could say sort important clinical events on a timeline, then it can help a physician or a clinician to understand better about, or at least faster about a patient's medical history. But if we can also do this on population level, then we can try to reveal the new patterns for a group of patients that has similar conditions or use same drugs, for example. Of course, there are many different challenges. So because we're trying to use EHR data, so as we are facing the same challenges that everybody wants to use EHR data. There are big amount of data, and the same patient could go to different healthcare organizations for different purposes. Even within the same hospital, the data could be scattered in different places and represent in different syntax, semantic, and etc. And also specifically for the temporal information, a lot of information are actually embedded in clinical narratives, such as clinical notes. So in order to extract the information out, we will need to develop automatic methods. Otherwise, it won't be scalable. In addition, many temporal relations are not explicitly stated in clinical narratives, but rather need to be inferred. I will use this simple example to illustrate what I mean. Basically, you can see here, here are 3 sentences from for the same patient from different notes. So the first sentence said patient's INR value is below normal, and then on the same note it says he has had some symptoms before the abnormal test, and then on another note it says on this date patient starts some treatment. So for example, I want to answer this simple question: did the patient experience the symptoms before the treatment? So in order to do that, we need to go through a few different steps. So first of all, of course, we need to recognize all the events. So here I already marked them, event 1 to 4. And also we need to recognize, the temporal information like dates and temporal relations. So after we do that, we still need to do some inference. For example, we want to decide, if there are analytical reference. So here, event 1, the INR value is below normal is actually the same event in the second sentence, abnormal test. And then we also need to, from the second sentence, we also need to extract some temporal relations. The event 2 was before event 3. And based on the first 2 facts, we can infer that event 2 was also before event 1. And another task we need to finish is we need to assign timestamps to different events. So here we assign 2 timestamps to event 1 and event 4 respectively, and combine all the facts. We can then infer that event 1 was actually before event 4, which is the answer of the question. Oh, I'm sorry. So event 2 was before event 4, which was the answer of the question. So as we can see, for this simple question, we need to go through several steps mentally to resolve it. If we want to do it automatically, it will be more challenging. So another scenario is, because we're dealing with EHR data, and as I said, data was scattered in different places. So sometimes, we can find information in a database, a structured database, and we can also find additional information from narratives. So in this example, we see, there's in the clinical note, it says fasting glucose test last week was 140, and 2 days after the test, something happened, but we don't know exactly when the 2 events happened. And we can go to the structured data, and we find that we think that that week, there was a glucose test. This is a line code for the same test with the same value here. So with the same test with the same value here, so that we can safely infer that these 2 things are referring to the same event. So we know the date of the lab test was June 12th, and then 2 days later, another event happened. So we can also calculate the date of that event. So our goal is to automatically, answer all these kind of temporal-related questions, and this is the system architecture. Basically, you can see the center component is called central, which is a time ontology we are developing. So this ontology sort of serves 3 different purposes. So for modeling, basically, we want to use this as a semantic model so that we can have a normalized representation for temporal information and temporal relations. For extraction, we are using this ontology as a annotation schema for the NLP pipeline so that the NLP tools can know what we want to extract. And also, we are building a reasoner on top of this ontology so that based on the extract information, we can also infer more information if possible. So here is a very high-level view of the ontology. I'm not going to go through the details, but you can see here we cover different perspectives of the temporal dimension, including, different temporal relations and frequency and granularity and etc. So after we have the ontology, the next step would be do the annotation or information extraction so that we can handle unstructured data. So we have developed these two called Semantic. Basically, it can provide an visualization GUI so that we can see the document to be annotated on the top, the ontology, and the annotation result. So here, different instances belong to the different classes are displayed in different colors. So we want to provide different kind of functions, for the user to browse, query, and edit annotated results. And we also provide 2 different modes. One is manual annotation. The other one is semi-automatic annotation. So for the manual annotation, we majorly use it as to create a gold standard corpus to develop an NLP tool. And for the semi-automatic annotation, we would like to connect to different NLP tools. As we can recall, there are 3 different components of the timer, and the third component is reasoning. So we are trying to build a API to provide different functions so that we can answer different kind of temporal relation questions. So here are a list of API functions. So the first function is to find the event. So basically, given some tests, we want to search to see if the event actually happened for a patient. And the second function is basically to answer the when question. So when did a specific event happen? And these two functions sort of answer the how long question. So how long what was the interval between two different events, or how long did a specific event last? And then these are sort of pooling questions to answer the to find the temporal relations between two events or between a specific event and a given time point. And the last function is sort of the comprehensive function. So give a set of events. Can we display, or can we sort the events by time, when they happen, and then display the events on a timeline? So based on the temper framework, we are actually developing different applications. So the first application is about the patient safety analysis. We first use medical device adverse event as a use case. So all the data are actually from an FDA CDC database called Manufacturer and Use Device Experience Database. And we use LST as a use case. So the goal of this research is to detect potential temporal patterns within these complaint files of similar adverse events. So here is the pipeline, how we did it. So from the FDA database, we extracted or gathered 230 reports for confirmed LST reports. And then we have human annotators to manually annotate these reports, for all the events and their temporal timestamps and temporal relations. And then we manually created a set of gold standards, not only for the annotation, but also for the answers of different time-related questions. And then we use the timbre reasoner to we call different queries of the timbre reasoner, and then we answer the same set of questions. So, and then we do some compression. So you can see the evaluation results for the timeline sorting. The accuracy is about 87%, and for the duration calculation is about 89%. So we also use this visualization tool. This is a very powerful tool developed by a University of Maryland. So we connect the tool with our data, and then we can see the event sequence pattern actually matches previous identified common temporal patterns for this use case. We also did some additional statistical analysis, and the result of this analysis also confirmed with previous relevant studies. So basically, the goal of this study is not to review additional new clinical insights, new patterns for LST, but instead we want, because LST is a relatively well-studied adverse event. So what we want to do is to use this use case to test our temporal pipeline to see if by using our tool, can we review valid temporal patterns. And we believe the conclusion of this study is that our tool can be used to review new patterns. So based on the results, we also try to analyze vaccine safety. And this project has recently been funded by NIAID under an R01 grant. So basically, we are also using a FDA database called VAERS, Vaccine Adverse Event Reporting System. And we found that the report from this database is sort of very similar to EHR but simplified. I have an example, but maybe I can show you. Yeah, I'll show you the example later. But basically, we found that what makes it interesting, or what makes it interesting to us, is that the temporal information embedded in the narrative were never used by other studies. So there are a lot of studies using the VAERS data because it's publicly available, but they are all using the structured data. Because we're in particular interested in the time dimension, so we also look at the write-up. So if read each report, there's not only some structured data tell us about what happened after vaccination, but they also allow the reporters, either healthcare providers or patients themselves, to write a short narrative, tell us more detailed information about what happened. So yeah, here is the example. As you can see here, from the structured data here, we do know the vaccination date, the first onset date, and some other timestamps. We also know the patient's demographic information, and also the vaccine information. We also know how severe the outcome was. Was the patient died? Was the patient disabled? Hospitalized, and etc. Here is the part we're very interested in. Is the write-up tells us, when the vaccination time, and also we can see not only it tells us the first onset date, but also there could be a set of events happen after the vaccination. But all this information, at least the temporal information, are missing from the structured data. So this is the part we want to focus on. So by using the timer system, this is what we want to accomplish. Basically, from the short report here, we want to extract all different kinds of temporal relations, including clinical events. So clinical events, specific dates, and the temporal relations, and etc. So then we can use the temporal reasoner to sort the related event over the timeline. So it will be like something like this. Then the result of our timer system will serve as input data for dynamic risk prediction. So I have a statistician, a collaborator, so he's trying to develop some powerful statistics tools so that we can do dynamic prediction based on, so these, for example, these are the input from timer result, right? So we know there are a set of events and we know when they happened and the duration in between. Then we want to see if we can predict if anything bad will happen in the next 10 days or so that we can warn the patient. Okay, so another application I want to introduce is how to use timer or the time ontology to semantically represent different kind of data, for example, eligibility criteria. This is in particular significant because, I'm sure you're all seen this paper published in September last year in JAMA by NIH. So NIH so the goal of NIH one of the goals is to increase the transparency in clinical trials, especially to ensure the shareability for clinical trial data. And one of the important steps toward this goal is to ensure the semantic interoperability among clinical trial criteria, so that the cohort of each trial can be more formally defined. And our current focus, of course, is also the time perspective. So we would like to see if we can identify temporal patterns in clinical trial eligibility criteria, and they represent these patterns with respect to our time ontology. And then, we can do different kind of things, like for example, if we can use a semantic query to represent the eligibility criteria, our next step is, if we can help clinical trial coordinators to retrieve eligible patients, maybe from EHR. So we did a preliminary project by using criteria retrieved from both clinicaltrial.gov and also the National Guideline Clearinghouse. And there were 600 trials that were randomly extracted from these two databases. And we found that there were 37 unique criteria. And then based on these 37 unique criteria, we created 16 temporal patterns. So here I list all the patterns. I'm not going to go through the details, but you can see, some of them are, about time, like before and after, and some of them we need to deal with, like a negation exception. And these are additional patterns, so there are 16 of them. I want to mention here, so for one criterion, usually it will involve more than one pattern. So for example, here for this one, it involves 5 different patterns for negation, for event happened at the same time, for exception, for before and start, and for offset. So basically, the offset defines what are the duration between two events. And based on this pattern, we can develop different kind of queries. So here we use all DL or all row to represent, for example, patterns. We also evaluate our patterns by testing on 100 additional protocols, 50 from trials, 50 from clinical deadlines. And from these 100 protocols, there were about 1,200 criteria, and 400 of them are time relevant. So we found that our defined patterns can cover 402 of time relevant criteria. So this gave us 95% coverage, which is pretty promising. And there are some things that we can't cover, so we are trying to refine our ontology to cover them. So for future work of this project, we're trying to evaluate the patterns using a bigger data set. And also, we want, as I said, we want to improve our ontology to cover more scenarios. And we want to connect to NLP tools so that we can do some kind of automatic classification of the patterns. Okay, so we have about 20 minutes or so, so I want to switch the gear to introduce a little bit about our work on ontology-based patient education. So this is actually related to public health informatics. So basically what we want to do is we want to see if we can use computer agent to help patients or users to find health-related information either online or inside of our database. So the motivation behind this project is that, if you, I'm sure we all went to a hospital once or twice, and then, we talk to doctors or, nurse to give us some flyers for education materials, but many of us wouldn't read the materials. And also a lot of these flyers are, way beyond at least my health literacy. So, I would sometimes I wouldn't able to understand the drug names or, the disease names and etc. And sometimes we go online, we search for information, but we don't know how much we should trust online information. And most of people choose to trust their healthcare providers, but the providers usually can only give us, limited time for, addressing our concern and our questions. So our thought is to develop informatics tools that, can help us to address all our concerns, or most, or a lot of our concerns, health-related concerns. So basically, we want to develop something like Siri, right? So by using Siri, Siri can answer us questions about the weather or our schedule. So can we develop some kind of healthcare Siri that can answer questions about a certain disease, about, if I take this drug, will something bad happen, and things like that. So that is the motivation of this research. So we started with vaccine. So basically, we want to use an ontology to model vaccine-related information, so that all the sentences are semantically annotated, and if someone asks some question about a vaccine, we can find we don't just give the patient the flyer, we give the patient the direct answer because we have an ontology backend. And by the way, the Apple Siri also uses an ontology as its backend knowledge base. FDA and CDC actually provide a vaccine information statement that, before vaccination, all the patients will be given this statement. But as I said, most people wouldn't read it. So our goal is to semantically represent these statements using an ontology, and we started with 6 different statements. So basically, there are 3 steps. First, we want to extract knowledge, concepts, and entities from these sources, and then we do conceptualization. We construct meta-level ontology, concepts and properties for the domain, and then we create instances. So first, this is a model, concept model for each statement. We would extract concept models, and then we aggregate all the 6 statements. And here are some sample classes and subclasses. So this is a very high-level overview about our ontology. We call it visual vaccine information statement ontology. And we published a paper, I think it was about 2 years ago, in Journal of Biomedical Semantic, to introduce this ontology. And after we developed visual, we also want to expand it ontology to cover more vaccines, and we found that the HPV vaccine is in particular interest because it's a very, it's a vaccine that has a lot of discussions, and it's instead of for babies, it's actually for teenagers. So we also want to deal with both parents and the patient. So we start to create an HPV vaccine-specific ontology, and we not just use the vaccine information statement, but also we use other resources like patient education books and online education materials. And we recently published another paper on MedInfo. I think it was last year. So basically, design an ontology, we need the design patterns. For the basic visual ontology, we already designed a few different patterns, but we found that there's something specific for HPV, so we expanded that pattern to create new patterns specific for this HPV vaccine. And we are still developing this ontology because to provide valuable education for patients and our users, we want to make sure that we can cover as much as possible. And HPV is actually a cancer-relevant vaccine. So we're currently working on expanding the ontology to cover the 6 cancer types that are relevant to HPV. So we still have some time. I want to briefly discuss about ontology evaluation. Ontology evaluation is actually important for all the ontology, but for our patient education ontology, we want to be very careful because we don't want to deliver false information to our users. So we started to develop this ontology evaluation system we called OntoKeeper. So we can sort of see how good the ontology is from different perspectives. We want to focus on, is the ontology useful? Can it be read? Can it be understood? Can it be trusted? And so here I just want to show some screenshots. Basically, we can the user of the system can configure the system. So I only want to evaluate from 3 different factors. Now from the social perspective, I can turn it off, and we can import the ontology, and these scores will be calculated automatically by the system. And also we provide a interface where domain experts can assess the quality or the truthfulness of the ontology contents and give feedback. And overall, we can give scores for each criteria, or we can have an overall comprehensive score of the uploaded ontology. Based on that, the ontology developers can further improve the ontology. So, here are just a few projects, because we have a limited time today, so I only introduce a few projects. As you can see, many of them are ongoing, so we're still trying to work using the technology to work on more projects. And in summary, ontologies and the semantic web technologies can provide solutions for different healthcare or biomedical applications. So we can use ontology to model clinical and biological data, so that we can conduct scalable querying and intelligent querying over the data. And we can also infer new knowledge based on what ontology has defined. Okay, so a little bit of acknowledgement. I would like to thank all my group members, my students, my postdocs, and also all my collaborators from UT Health, from UCSD, Mayo Clinic, University of Michigan, and etc. I believe, okay, also my funding sources, from NIH, AHRQ, CPRID, and ONC. And a little bit about advertisement. So we are organizing 2 oncology relevant workshops this year. The first one, it will be Kansas City, and I think the deadline is in June. And the second one will be in UK, and deadline is also in June. So if you're interested, please check out our website and submit your papers. I think this is my last slide. Thank you very much. Any questions? Let me see if I can go back to the. Yeah.
Please feel free to ask any questions, anyone. Okay. I guess there's no questions, Dr. Tao, but thank you so much for your presentation.
Sure.
And our next webinar will be Thursday, June 8th. Thank you so much.
Thank you, everyone. I'll send you my slide very soon.
Yes, that's fine.
All right. Thank you, everyone. Bye.
Bye.